Rotational motion. To learn about the rotational motion, we should know what is torque or what is couple. The ability of a force to produce a rotational motion is called moment of force or torque. The torque is given by R cross F, where R is a perpendicular distance measured from this axis of rotation and F is a force applied to this bob. As the direction of the force changes, the direction of the rotation also changes. What is couple? The two forces equal in magnitude but opposite in direction acting at two different points of a body form a couple. In this GIF, these two forces are equal in magnitude but opposite in direction and they are acting on a two different points, and due to this it forms a couple. This couple produces purely rotational motion and no translation motion because the net force acting on a rigid body is zero. So once this couple produces a rotational motion as shown in this GIF, it is found that the net force acting on this rigid body is zero. That is, the torque must be constant. In rotational motion, the linear speed of a particle of a rigid body moving in a different circles at any instant are different. So, in this GIF, you can see that this object is rotating about a axis which is passing through the center, and the arrow shows its tangential velocity, and it is different at different position of this rotating body. So these are arrows which can show the direction of the linear velocity at different points. Moment of inertia. What is moment of inertia? Before that, we should see the inertia in a translation motion. In a translation motion, mass of a body is measure of a inertia. Inertia is that property of matter that causes it to resist its change in velocity, that is a speed or its direction. So, a quantity that measures the inertia of a rotational motion of a body is called rotational inertia or moment of inertia. In this GIF, we see that all the objects are getting rotated about an axis passing through its center. If you oppose this motion about this axis passing through its center, is called as the moment of inertia. Let us prove that moment of inertia as an analogous quantity for mass. For that, we will take few equations for a linear momentum. For example, torque is equal to force into a perpendicular distance. Force can be written as mass into acceleration. So we are getting the formula for the torque is R into M into A. Linear momentum is always given by the alphabet P, and that is equal to the mass into velocity. The force for a fixed mass can be written in terms of linear momentum as change in momentum upon time. Change in momentum is nothing but the final momentum minus initial momentum upon time. So equation can be written as mv minus mu upon t. V is a final velocity and u is the initial velocity. Same way, we'll consider the one more equation, that is a kinetic energy is equal to half mv square. So in all equation, it is found that mass is a common term. M here in this equilinear momentum, here is also m and here is also m. So in order to have their rotational analogous, we need a replacement for a mass. For example, consider a door with hinges, and when we open the door, we give a certain angular displacement to it. Consider this is a certain angle given, or the angular displacement given to this door of opening. So the effort needed for this depend not only the mass of the door. So consider these dots are nothing but some mass distribution of this door. but it also depends upon the perpendicular distance measured from this axis of rotation. These horizontal arrows are the perpendicular distance measured from this axis of rotation up to a certain mass distribution of this dome. Thus, the quantity analogous to the mass includes not only the mass, but it also takes care the distance-wise distribution of a mass around the axis of this rotation. So suppose this is the axis of rotation. The distance measured from this axis of rotation to a particular mass also plays a very good role in a moment of inertia. Let us derive the expression for the kinetic energy of the rotational motion to prove that the moment of inertia is an analogous quantity for a mass. Let us calculate the rotational kinetic energy of a rotating body. We know that rotational kinetic energy is the sum of translation kinetic energies of all the individual particles. So consider the figure of a rigid body which is rotating with a constant angular speed about an axis perpendicular to this plane of paper. And let us also consider this rigid body consists of n particles of masses m1, m2, m3, m4 and so on mn at a respective perpendicular distance, say r1, r2, r3, r4, rn from the axis of rotation. So, as the object rotates, all these particles, that is the particle mn, m2, m3, all these particles perform a UCM, that is a uniform circular motion with the same angular speed omega, but different linear speed v1, v2, v3, v4 and so on vn. As the body rotates, all these particles perform uniform circular motion with the same angular speed but different linear speeds, and it is given by the velocity of the m1 particle is given by v1 is equal to r1 omega. Velocity of mass m2 is given by v2 is equal to r2 omega. Velocity of mass m3 is given by v3 is equal to r3 omega and so on. Velocity of a mass mn is vn is equal to rn omega. The translation kinetic energy of a first particle is given by kinetic energy of mass m1 is equal to half m1 v1 square. We know that v1 is r1 omega. So substitute the value in this equation, we can get the kinetic energy of a mass particle m1 is given by half m1 r1 square omega square. Translation kinetic energy of a second particle mass m2 is given by kinetic energy of 2, that is a mass particle 2 is given by half m2 v2 square. v2 is r2 omega, so equation can be written as half m2 r2 square omega square. Similarly, we will consider the translation kinetic energy of a third particle mass m3 can be written as kinetic energy of a third particle is equal to half m3 r3 square omega square. And in the similar way, we can find out the translation kinetic energy of a nth particle, that is kinetic energy of nth particle is given by half mn vn square. Just substitute the value of vn, that is rn omega. We get the value is half mn rn square omega square. We know that the rotational kinetic energy of an object or a rigid body is a sum of individual translation kinetic energy. So if you add all the individual translation kinetic energy of all the masses of rigid body, we can get the rotational kinetic energy is equal to half m1 r1 square omega square plus half m2 r2 square omega square plus half m3 r3 square omega square plus dash 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 plus half mn rn square omega square. Take the common term half omega square out of the bracket. We can write down rotational kinetic energy is equal to half into the bracket m1 r1 square plus m2 r2 square plus m3 r3 square plus dash 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 plus mn rn square close the bracket into omega square. Here we substitute the summation of m1 r1 square plus m2 r2 square dash 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 plus mn rn square as a I, or we can also write down I is a summation of the product of mass and square of perpendicular distance from the axis of rotation, and we just give the suffix as a I factor. So I can be written as summation of mi ri square, where I equal to 1 to n, and if we just substitute the value of I in this equation of a rotational kinetic energy, we can rewrite the equation as rotational kinetic energy is equal to half I omega square. Thus, we compare the rotational kinetic energy formula with the translation kinetic energy formula. It is found that half term is a constant in both the equation. Omega square is a angular velocity of a rotating body in a rotational kinetic energy. V square is a linear velocity of a body in a translation kinetic energy, and the mass in a translation kinetic energy act as an inertia, and if you replace this mass with the I factor in a rotational kinetic energy, so we can say that I is a inertia for this rotational kinetic energy. So we can write the rotational kinetic energy formula as a half I omega square, and we can say that the rotational kinetic energy is analogous to the translation kinetic energy. Let us learn some factors of moment of inertia. The object consists of a finite number of a particle performing a rotational motion. Its moment of inertia is given by I is equal to summation of mi ri square, where I stands from 1 to n. So the moment of inertia I is defined to be a rotational inertia, or the moment of inertia of the object about the given axis of rotation which resists the rotational motion. It is clear that the moment of inertia of an object body depends upon first its individual masses m1, m2, m3, so that the mth, and the distribution of these masses about a given axis of rotation at a particular distance, say r1, r2, r3 up to the rn. So for a different axis, it will again depend upon the mass distribution around that axis and will be different if there is no symmetry. So this axis of rotation can be vary, and the mass distribution will also get changes, and hence the moment of inertia of this rigid body may change. For a homogeneous rigid object of a mathematically integratable mass distribution, the moment of inertia is to be obtained by integration as I is equal to integration of r square dm. So if the mass particle is very small, that is just a very small particle, and it is a homogeneous rigid object, the moment of inertia of such body is given by I is equal to integration of r square dm, where r is a perpendicular distance of that object from the axis of rotation. If the integrable mass distribution is not known, and it is not possible to obtain the moment of inertia theoretically, but it can be determined experimentally by doing the various experiments.